Hello and welcome back to Precalculus. The goal for today is to learn about logarithmic functions. So last class we learned about exponential functions, and now we're going to learn about logarithmic functions. Now, logarithmic functions are gonna wait for a second because we first need to learn about logarithms in general. And the way I go about it is I say 2 plus 3 is 5, 5 minus 3 is 2, and 5 minus 2 is 3. And you're looking at this and probably go, really? Yep. 2 times 3 is 6. 6 divided by 3 is 2, and 6 divided by 2 is 3. Are we all learning? So addition and then repeated addition is called multiplication, and now you have repeated multiplication is called exponents, right? So 2 cubed is 8 because 2 times 2 times 2 is 8. Now, cube root of 8 is 2. Okay, great. How do I recover 3? Right? Is there mathematical operation, right? Because I was always able to recover both of the input values, right? I would like to now recover 3 somehow. And this is where log base 2 of 8 returns 3 as a value. So this is just a mathematical operation that calculates value given 2 numbers as an input. You give 2 numbers as an input, you compute a number. You give 2 numbers as an input, you compute a value at the end. Well, for log as well, you put in the 2 values in, and out comes, right, in this case, 3. Now, we just want to learn as much of these important things about these logarithms and see where they are from and how to compute them and all of these kind of things. But in all honesty, we should not be discriminating against logs as they're something special or different than any of the other operations that we have, because they are not. So first, for notation, when you are writing a log function, you can see that I am using over here these lines, right, as a guide. And if I say log, see, 2 is a small, and then 8 goes here is equal to 3, right? So you can see the spacing, right, which is different than log of 28, right? That's gonna have something else later on. So this number needs to be small, right? It needs to be in the middle of this line that goes underneath log and 8, right? Which is like the main line on which everything rests. If you are using improper paper for mathematics, meaning the lined paper, right? I used to be kicked out of classroom if I don't have the square grid, by the way. So I would never dare to write mathematics on the lined paper. It's just, I can't. I've been scarred for life. They just say, "Oh, you don't have the notebook? Out. School is not for you. Go play ball or something," right? So, yeah, proper spacing is important in this case. So you know that this is a very, very small 2, right? It's like an index, like when you write x1 or x2, right? You don't write x2, you say x2. So that's the same way you're going to say log 2 of 8. But technically, we are going to now say we are talking about log a of b. equals c. So this is, as we can see, something that it's related to exponents, right? And in some sense undoes the exponents. Ooh, that's a special language. We did use the word undo with a particular concept in chapter 1. Anyone? The word undo.
Inverse?
Yes, very good. So now, here in blood, we learn that logs are inverses of exponents. Yes, logs are inverses of exponents. Technically, they undo each other. So if I say 10 cubed equals to 1000, I can also say that log base 10 or 1000 equals 3. We can also say cube root of 1000 equals 10, but we are not observing that particular function right now, so we're not going to do that. So since we now discovered this, we get to learn this insanely important equation that you will be using pretty much in every problem when we do with equations. And if you don't learn it, you're technically doomed, which says a raised to b equals c converts into log base a of c equals b. Like, this is worth tattooing on your arm.
So this is what the inverse of it looks like?
So you can convert between, yes, you can convert between two forms. Now, to compute logs, you need to consider exponential functions, right? Consider exponents. That's one way. And obviously another way is calculator. We do not compute these by hand because they're really nasty to compute, which is why a lot of people are really scared of them. But technically, mathematically, they're a joke. Computation-wise, they're terrible. But algebra-wise and the rest, they're really, really pleasant, and we love them dearly. So let's see. If I say 5 squared is equal to 25, I can write log of base 5 of 25 is equal to 2. So as you can see up there in the conversion, the answer of the log is the exponent of the exponential form, right? Because on the left you have exponential form in red, and on the right you have logarithmic form for the same ABC numbers. They can be written in either form. So you might be wondering now, how much is log base 2 of, let's say, 1/4? Okay, well, let me convert this and just see if I am in any way able to answer this question. My base is 2, I have this unknown exponent, and the result needs to be 1/4. Is there a way for me to make this to be a base 2? Yeah, I can write this as 4 to the minus 1, and then I can write it as 2 squared, and then by the properties of exponents, those two multiply. Aha! Aha! So that's -2. Awesome. And you're like, do I have to do this every time when I have a log? Well, you won't be able to, because most of the times they don't line up this nicely, right? Like if there are decimals around, you're doomed. I mean, you have to have computer or know something from calculus to bypass this. So certain logs, right, where we say calculate without use of the calculator, yeah, in that case, you can probably do something like this and figure it out. Let's take a look at another log. Log base 3 of I don't know, 81 is equal to what? Well, 3 to what is 81? 3 to x is equal to 81 can be written as 3 to the 4th. X is 4, so that's a 4 right there. Nice. Can I use my calculator to compute these logs? Yes, but you have to be very careful. So your calculator does have an LOG button, but it's a very special button. It only works with a base 10 logs. So can you compute the problem you see on top? The answer is no. Most calculators cannot directly compute the problem above because the LOG button is the log base 10 of some value that you plug in, not log base 3, right? So you have to be careful about that, which is why we learn what we call the change of base formula. Now, before I go in there, I also want to introduce the natural log, ln of a, which is actually the log base e of whatever number you put in there. It's just a lazy notation for the log of base e. Remember the special number e from last class? So if your base for the log is that special number e, then we use ln rather than log. It's a lazy notation, guys. Between this notation and this notation, you have 2 characters less to write. That's it. There's no other difference. You just have less writing. Now, why would we go out to do this? Because our application in engineering and sciences across the board has this one, I guess 90% of the time, and has this one 10% of the time, and you never see any other ones. Which is why your buttons on your scientific calculator contain only LOG and LN button. Now you will here and there find a calculator where they went out of their way to program the calculator so it can put in anything in, including this problem above, but those calculators are very, very rare and you have to look very hard to find which calculators actually do that. But your TI-83, 84, 92, and like they don't do that. The more advanced calculator is, less log buttons it has. I have seen log scientific calculators, they have only LOG, and I've seen them only with LN, right? Only having one. And the reason why is this change of base formula which you guys memorize and then you use it if you have to calculate logs that are not base 10 or something. Oh, by the way, I just noticed that I never wrote here. That's just LOGA. So let me just go back to this, please. I'm sorry. Focus here. Focus here for a moment. If there is no base, the base is 10. If there is no base, the base is 10. If it's ln, the base is e. All other bases have to be written in, like I did before, log base 2, log base 3, log base 5, anything else. So if there is no base, base is 10. If there is ln, the base is e. So those are the two that you must memorize, which is why I have them kind of separated here. And then the log base, this one, right, will have log button in your calculator, and the ln one has the ln button in your calculator to compute these. So natural log has base e, and the log base 10, right, it just has no base in it, it's just empty. Now, if you run into any log that has different base than e and 10, so let's say log a b like this, you can change the base into log b divided by log a. This is the 10 base, and you can use your calculator. Or ln b over ln a. So this is your change of base formula, and this is how you can use your calculator to compute log 7 of 39. You convert this into log 39 over log 7, and then you can use your calculator. Remember to close the parenthesis after 39, or your answer will be garbage. Log 39 closed parenthesis. See, when you push the log button in your calculator, it opens the parenthesis. Then you put 39 in it, and then you have to close the parenthesis. Calculator doesn't know when to close it. It will close it when you say so. So log of 39, close the parenthesis, divide that by another log of 7, close the parenthesis, and you should have 1.883. And this is approximation, obviously, because these decimals will go on forever. So you can put squiggly equal signs if it makes you happy. If you go in your calculator and try ln of 39 over ln 7, you will get the same number. There's no difference. That's why in red up there, you have both of those available to you, and whatever you have, right? Whatever you have will be calculated equally, right? Whether you use logs or you use ln's. So it would be good for you to practice computing, let's say, log 8 of 46.19. Just you put whatever nonsense in there. If you have the answer, just say it. Did anyone compute this? Choose your calculator, quickly punch the numbers in, you're done. Same like the problem above. You guys awake?
I did it in the calculator, but I don't know if I put it in correct because my answer is like 0.0090.
0.0090, like this?
Yeah, I mean it goes on longer, like two. It goes 0.0090202199.
Nice. Okay. Anyone else with a different
Yeah,
number?
I got 1.843.
843. Okay. Now, I would like you all to try again. Make sure that you are either using log both times or ln both times, and make sure you close the parenthesis after this one. Usually that's where the mistakes are, if you don't close the parenthesis, because in that case I'll show you what the calculator understands once we are done with this calculation. If you plug it in wrong way. Do we have anyone else confirming either of the two numbers? Or any of the answers changing to another answer? Maybe another answer that's not written.
I did it again with like keeping the parentheses in mind, and I got the same thing. But at the same time, I don't know if I'm like my calculator is putting
I,
it
I
in.
don't know if it's right. I haven't done it yet. All right, so let's see. So this problem is going to be ln of 46.19 divided by ln of 8. So I'm going to plug in ln of 46.19, close the parenthesis, divided by ln 8, close the parenthesis. I'm getting 1.843. I mean, approximated, because there is another 169,547, blah, blah. Now, I'm going to try and get the answer above to see if the parenthesis was a reason. 46.19 immediately divided by ln of 8. No.
I
How,
don't know what I did. I don't
how did
know.
you manage? I'm trying hard. I'm trying hard.
I don't know what.
Divide by log 8. No. All right, I don't know what you did. It doesn't work on this number, right? It's definitely the one below. So, guys, when you have the log of A and B, you have to type in the log, which is the button. It will open the parenthesis. Then you put your B, and you have to close the parenthesis, which is another button you click. And then you do your division sign, which is a button. And then you have your another log button, which opens the parenthesis automatically. Type in A. You don't technically have to close the parenthesis here, but it's good. So usually this is the one that kills the grade, because students usually don't close this parenthesis. And if you miss that parenthesis, then you are not computing what you want to compute, because the calculator follows order of operations. And if you don't close that parenthesis there, the whole thing goes nuclear. So log base 7 of 13, right, is going to be, let's say, ln 13 divided by ln 7, which means ln of 13 divided by ln of 7. Now, if you don't close the parenthesis, the problem that you are actually solving is ln of 13 divided by ln of 7, and that is not the same, right? Because you see that 13 is getting divided by ln 7, not the entire ln 13, right? The ln 7 then only divides 13 if you don't close the parenthesis. So the calculator thing has to be right on spot, and it's the only way to get the answer. So in this case, you should have 1.3181 about that value. Awesome.
I was putting it in completely wrong, like completely wrong. And I redid it the right way and I got the 1.8431.
Oh, did you put this number on top and then this now on the bottom?
No, I just didn't put it in the correct format, like the log B divided by log A. I just put log and then the answer in the base.
Ah, okay. You did not have a second log from the formula.
No,
Okay,
no.
now I get it. So,
Log A
yeah.
and then the arrow and then put the exponent there.
Okay, cool. So now we know, right? See, this is why it's important for us to talk during the class so that can be cleared up, because it would really be bad for you to find that out on the test, right? Now is a good time to fix the problems. So we see that there is a separate log for B and then the separate log for the base A. So these are two separate logs that have to be placed in a calculator. Awesome. So now that that's cleared up and now we know, right, how we compute logs, because all of this, all of what we're done here is log as mathematical operation. You plug two numbers in and it spits out the third number. Remember what we said, 2 plus 3 is 5? You feed in two numbers and this operation makes those two numbers into a 5, combines them into a 5. 2 times 3 combines the two input numbers, combines into 6. Well, now log 7 and 13, right, combines that into 1.3181, whatever. So now we understand that log is just another operation and it fits this narrative of opposite operations, just like addition and subtraction are opposite of each other, multiplication, division. So now you have that exponents and logs are inverses, opposites of each other, which is why sometimes, for some cases, you can actually go through exponential function, right, if these numbers nicely line up, and you can compute the value of your log through converting it into exponential. Now, that doesn't happen all the time, so we will use calculator to get those other values when we need. Well, now it's time to introduce log function, logarithmic function. Just like for all others, logarithms are ways to compute, right, two numbers into a third number, to combine two numbers, right, through logs. So they are not functions by default, just like addition is not a function on its own. So if I have 2 plus 3, you're not going to call that function. But replace one of those with x. Ooh, it becomes a linear function, right? Aha. So I need to have an x in order for the logarithmic computation, calculation, whatever you want to call it, for it to become the function. So I'm going to define my logarithmic function as log base a of x, right? So now when I have the x present, right, it becomes a function because all of your functions have a variable in it, right? Other than a constant function, which is just like, y equals 3, then that's just, there's no x there. But all others do have x somewhere. So now, when you are looking at this logarithmic function, we just want to go through the whole spiel of those things that we know from chapter 1 and see what are all of the properties, right, and truths about logarithmic function. By the way, everything that holds for log a of x is also holding on for ln, because in that case a is e. So anytime I talk about log, I'm talking about ln. Anytime I'm talking about ln, I'm also talking about a log. Please remember it once and for all that ln a or ln x is equal to the log base e of x. This is a lazy notation. Lazy notation. There's nothing special for these. There will be different for those. Nothing. All of the rules everything exactly. This is just us being lazy and writing 2 letters less than what you see on the right hand side. We can have completely the same mathematics and rules and everything from algebra all the way to calculus 10,000, right? Without ever making this into ln x. Just keep writing it as log base e because there is no difference whatsoever. So anytime I say log for anything, it immediately follows as well for ln, because ln is just log with a special base e. So, and we specify that and set it aside because it is so frequent, as we are going to see later in our applications. So what are the properties of logarithmic function? Well, the first thing that we are going to learn and memorize, obviously, is the graph for this function, which has to look the same as exponential, except it needs to be reflection on that y equal x. So it's going to go through 1. And because the exponential function had a horizontal asymptote at 0, this one is going to have a vertical asymptote at x equals 0, which will logarithmic function follow to negative infinity down. So what are my specs over here? Well, I see the graph. Domain is 0 to infinity. We see that on the graph. There are no values on the negative side of x-axis. There are no values there. And then, since there is a vertical asymptote at 0, we also don't have a value at 0, which is why we have a parenthesis for 0. 0 is not included. So it's what we would just say positive numbers are in the domain of the log. Only positive numbers. For the range, it's all real numbers, because you see that all of the y values, right, are represented from negative infinity to positive infinity. So all of the y values. Now, if you are to compare this to your a to the x, right, the domain was negative infinity to positive infinity, and the range was 0 to infinity, right? The opposite. Yeah, because, right, your inverse functions swap domain and range. So for exponential functions, these domain and range are swapped. So that all fits, right, in the narrative from before. X-intercept, use your eyes over there, right? 1, 0. Y-intercept, none. Clearly, you have a vertical asymptote. We know that you can't have function cross it, so there is not going to be any y-intercept. Vertical asymptote at x equals 0, and Hasa none, because there are no horizontal or slant asymptotes in this function. These are your basic specs: domain, range, x and y intercept, and all of the asymptotes. And you have the what we call the vanilla graph, right? The default basic graph. So what do we do now with the graph? Yeah, 1.6. Shift it left, shift it up, stretch it, reflect it, right? So I hope you see that the chapter 1 is actually applied to each one of your functions that you will ever learn. Trigonometric later, hyperbolic, right? So no matter what function you learn, you always go back to 1, 6, 1, 7, 1, 8 to do the function composition, to do the shifting of functions, like all of these things. That never goes away. Never goes away. So, what do we get? Well, 1.6 applied to log a of x. Meaning transformations, shift, left, right, up, down. All of those that you learned, all 6, apply to the log because logs, right? It's a function. Oh, by the way, we see it's a function, right? Because it passes vertical line test everywhere. We all see that, hopefully. So we don't have to debate whether the logarithmic function is function. Apart from the title telling us it's a function, you can also see in the graph that it passes vertical line test everywhere. So yes, it is a function. We don't have to think too hard about that. Now, let's say you have your f of x equal log 2 of x minus 1 versus, let's go with the g of x over here. You can use any letters, right, for function, x minus 1. Is this the same? Come on, is this the same?
No.
Wow, that was really flat. I was more likely expecting hell no, right?
Right.
Because it brings more emotion, right? Would you agree?
Mm-hmm.
So what kind of transformation do I have here?
That's horizontal to the right.
How much?
1.
Good. And how about on the other one?
Vertical down 1.
Good. Now I need everyone to stare at this and realize that these parentheses are not there for decoration, right? They serve a clear purpose, and you can see that by PEMDAS, right? Because logs are related to exponents, all of this is glued together, and then you have minus 1. So that's somehow that f of x minus c, right? Where over here, because this is a group, right, then all of this is like a 1 unit, and you have your 1 attached to x, which is why this is this situation. And this is your horizontal shifting, and this is your vertical shifting. So it's not the same. It's not the same on whether you have these parentheses or not. And you will be held responsible, obviously, on the exam to do that properly. So now I can graph all 3 on the same coordinate axis over here. The vanilla one, obviously, is going to go through 1. That's just log base 2 of x, vanilla case. And then I have move 1 unit to the right. That's the red one. Okay, not a problem. My actually asymptote will shift. And I will now be going through 2 instead of going through 1 from before. Because everything shifts. Everything shifts this way. So, whee. And that's my log 2x minus 1. The blue one is down 1. So the blue one is going to go through here, and the blue asymptote stays where it is because you're just taking this asymptote and shifting it down. So the blue one is going like this. And the point that it goes through is 1 and negative 1. So that's your log 2x minus 1. Now, very often in the book, you are going to find this written negative 1 plus log 2 of x to kind of further avoid confusion between these two worlds. And that's technically the only thing I need you to be very careful about, right? this vertical shifting that you might confuse with whatever else. So now we have all of the other reflections, right, on x-axis, y-axis, stretch it, up and down and shrink it and all that kind of stuff. Like all of that is back. So graph f of x as -3 log base 7 of x plus 4. Okay, I have a lot to unpack here. Well, luckily, this is up 4. We don't have to think about it. This is just going to be your vanilla state. Whether this is 2, 7, or 100, it's not humanly possible to do an amazing job in graphing those, because they will literally be just like this. Like which one? Like they're all close. So as long as you have one of them going through one, you can call it log 7, you can call it log 100. It doesn't matter, right? It's not humanly possible to do an amazing job in distinguishing between 7 and, let's say, 9 and 25, whatever base you have. You just draw the regular shape. And finally, we have a 3, which is vertical stretch. And then we have this one. What kind of reflection is this? Come on, guys, it's in front of the entire function. This stuff is on your exam tomorrow. Like you should not be thinking about it. You should just spit it out, and we are moving out immediately.
Reflection on x-axis.
Thank you. I'm getting concerned over here. Should we move the test for like another month or something? Because this should really be like zero thinking. Is just, what's your name? Mark, and that's reflected on x-axis. Like instant response. Okay, we start with the vanilla case. So this is going to be my log 7x. And remember what I said, always reflect first. If there is reflection, please reflect, then start shifting. So a reflection over here, again, it's still going to go through 1. Reflecting on the x-axis is just going to go like that. So this is your negative log 7x. Now you can stretch it if you want to. You can shift it or stretch it. Let's stretch it. Still going through 1. It's just going to go like this. There we go. Let's say that's 3 times. So this is -3 log 7x. And the final stage, move everything up 4. Remember that your point was here. Now it's going to go 1, 2, 3, 4. It's going to go there. That point is 1, 4. And you're going to have the same graph. My cooling pad is making it very difficult to draw. Come on. Okay, and something like that. We don't know where it crosses. We can compute later when we learn equations, but it's going to cross somewhere. This is the point that I'm interested in for full credit, right? And this is -3 log 7x plus 4. Now, if it was parentheses, instead of going up, you will go left. But because it's not parentheses, you are going up. Now, in a book, you're going to find this question under 4 minus 3 log 7x. Maybe you want to, take a look at this, because it's just in like rearranging terms in algebra, in arithmetic, whatever. Instead of writing 2 minus x, you write minus x plus 2. It's the same thing. It's the same thing. It's just, you know, one is valid because it has less symbols. The other one is valid because x is first, constant is second. So they're both valid. It's just, you know, which form do you need if you are canceling? So, yeah, that's it on the logarithmic functions. Believe it or not, you just get to shift them and move them, and we can have some cool properties. Now there is a 3.3 section that teaches you the actual properties of logs, but there are some cool things that we can actually learn now that help a little bit with calculations of logs. Log of any base of 1 is equal to 0. Log of any base of 1 is equal to 0. So what do we have to prove that? Well, you can just say, how about if I convert this into my exponential form? Okay, a to the 0 equal 1. Oh yeah, I know, I learned that in algebra. Yeah, that's cool. Move on. Okay, another one. Log a of a is always equal to 1 if the numbers are the same. So log 3 or log 100 of 100. And that is bloop, a to the 1 is equal to a. Well, yeah, that's another algebra case that we know. Now again, all of this works for ln as well, because when a is e, then you have ln of e equal 1, right? Because if you set a to be e, then this a must be e as well. So ln of e is 1. It's not a special rule. It's this rule just written as e's, right? So if you replace your a's, so instead of using, let's say, 3 and 3, you're using e and e. Well, log e can be written as ln, and then you have that e, so ln of e is 1, following the same rule. The other two rules, a little bit spicier to understand in the beginning, but they work the same way. Actually, no, this should not be spicy to understand. Who can tell me what this actually is? Let's see who's ready for tomorrow, because this is on the test tomorrow, not with logs, but this is definitely on the test tomorrow. What is this? Come on.
Are they inverses?
Yes. It's a function composition to check if two functions are inverses of each other. Yeah. You're 1.8. Right there. So what do I have? I have the exponential function stuck in a log. When they cancel each other out, you have x. Right? This is literally f composed with the inverse giving you x. It's like the 1.8 is just 1.8 applied to logs. Sure, in our class in 1.8, we dealt with, you know, these courses. I mean, sorry, the function we dealt with functions that are like a square root of x with x squared, or cube root of x and x cubed, and you know we dealt with those in 1.8. But now you can expand your 1.8 repertoire with these guys. So I'm just going to point out that function composed with the inverse is equal to x, and inverse composed with a function is equal to x, which are just those basic ideas from from 1.8. Again, further kind of reinforcing this knowledge that this is, like logarithmic functions are the inverses of this. Good. Well, that's it, guys, for now. Next class, right, on Tuesday, we're going to explore logarithms more when we learn a little bit more of those. And we'll do way more examples, right, in this category here, right, where I can say, okay, how much is log 7 of 7 raised to the x, and you just say, oh, it's just x because it's literally this formula, except instead of b, I'm writing a 7. So, we'll take a look at some of the numerical exercises because now we're just going to go and do the review, another review for the exam that it's tomorrow. And we'll be back with exponential functions and logs on Monday. Bye.